can change the discrete signals to the analog signals. If we have a discrete signals, then if we want to change to the continuous time, we use the function about the hold, and the hold, that means you keep the hold of the part, then they connect the point to point, and after that you can see what is the continuous signal that you have. Obviously you have some error exists, but you can approximately find the continuous time. This is the show the example between the discrete time that they showed by plus. Blue line is a use the hold to make the discrete to the continuous, and the blue line is a mean value of the hold signal, and if you see, obviously is a very close to the origin signal in the continuous time. We find the by zero order holder. Another thing that or function we can change the discrete to continuous time is a first order holder. First order holder and the zero order holder we will discuss later, but just know about the definition about this function. That means change the digital to analog. That's it. Here that means if you have a digital signals with the hold is a zero order holder or first order holder, you can change to the analog signals. Here you will see, if you have an analog signal, you want to change to the digital, use the sample and the quantizations plus coding 2, but the coding and the quantization will eliminate for this course. If you have a digital, you want to change to the analog, use the holder. This is the tracking mode, hold mode. Tracking mode exactly the same as the show system in the transient part. Hold mode is showing the steady state part. And they show fast sampling and the high resolution quantize produce digital signal that close model that analog. And we saw if you have a very small sample time, this discrete time close to the analog, but they need the expense rise with the speed and increase the CPU and storage cost, because you must store a lot of data. And here they said in this course the quantization and the coding will eliminate, and just only for changing the analog to digital use the TS or sampling. Now here's a block of the controllers. If you have a block of controller, that means this one is a digital, you need a converter. Digital go to the analog here, because your plan is analog, there's a converter, and the digital analog they go to the plan analog. Sensor is analog, doesn't change anything here, but the analog is in the sensor, and you go to the digital system, that means another converter to change the analog to digital, then you can go to the controllers. Meaning here if you have a digital control, here you have analog, here you need the digital change to analog, that means you need some holder here. Here you have an analog want to change to the digital, you need the sampling. Quantization we eliminate. That means this converter here is a sampling, and this converter here is a hold system. Okay, here they eliminate the quantization, and here you have a TS, here you have a holder, and which holder we discuss later, zero order holder or the first order holder or impulse order holder. This schematic that you see in the continuous time, you have a differential equations of the time. Now you have a differential equations in the discrete times. Before you had the y dot t plus y dot t, then with the Laplace we go to the transfer function. Here you will learn with the z transform you go to the discrete transfer functions, and here you find the transfer function in the s domain, for example s plus 1 and s3 plus s2, and the inverse Laplace we go to differential equation. Here by the z inverse you go to the differential equation, and the same thing from the transfer function you can go to the discrete state space, or from the discrete state space you can go to discrete transfer functions, or directly from the different equation you can go to the discrete state space, or from here you go to the different equation. All of this we will see together. And in the end, when you here actually is a EE312, you learn the Laplace, inverse Laplace, how you change to the transfer function to the steady space, and the steady space to the ordinary definition. EE323, you will learn how to make the Z transform, inverse Z transform, steady space, and how you change the steady space to discrete. Then in the week 6 you will easily change directly from ordinary differential equation in the time domain you go to the discrete domain, this and vice versa. Or if you have a transfer function in the S domain, easily you can change to the Z domain, or steady space in the time you can go the steady space in the discrete time. This is the week 6 and week 7 we saw together. Okay, here in the S domain, control in the S domain, my plan in the S domain, and the HAS or the sensor in the S domain, and the input you have the S and the YS. That means the transfer function YS divided by RS will be my system. Here I change the only control part to the digital part because I want to learn digital control system. If I change this one to the digital, you learn here you need a one converter digital go to the analog because my system in the analog or in the time domain or in the S domain. Here they have a sensor in the analog, you need the analog digital go to the discrete time in the control system. Okay, here repeat again. If the sample time is sufficient small, then the digital signal should be close to the analog signal so that the output should be similar to the digital or with the analog controllers. This one we saw. If the TS is very small, TS is between these 2 points is a TS. Here is a TS. It's very small digital and analog is close together. Here are some general rules. An analog controller and its discrete version or digital controller give a similar result when the sample frequency Fs is much smaller than the bandwidth of the system. This explanation exactly the same as here by show the frequency and the bandwidth. Usually more than 10 times, that means 10 times of the frequency of the signal should be less than the bandwidth of my system. And another rules, the same rules but with the TS they explained, an analog control and a discrete version give a similar result when the sample time TS much smaller than the constant T of the system. TS is very smaller than T or 10 times the digital, and the analog will be similar together. Here they show the two system is a time responsible the system 1 and the time system responsible the 2. Now here is I said in the week 6 we will check together. We will not use any converter digital to analog and analog to digital. Directly we change my plant and my HS to Z domain. If I change directly in the Z domain, I don't need any converter. Here the name is discretization. 7 or 8 method I will tell you how my system in the S domain, for example transfer functions in the S domain, easily can change to the Z domain. Then I don't need any converter because my control is in the Z domain. I change my system or my plant to the Z domain and my sensor in the Z domain. Here they said if you have a plant in the S domain with the discretization go to the Z domain, and if you have a control system in the S domain with the discretization you go to the discrete time or the control time. What they say here, if you have the closed loop system, here is a controller, here is a system or the plant, here is a feedback, all of them in the S domain. Here is the S domain, my system the S domain. I can design my controllers in the S domain, then with discretization I can find the CZ, or I can change my plant to the Z domain. My plant, that means transfer function, go to the Z domain. I design the digital control in the Z domain, then I can find the transfer function about the closed loop. Both of them is correct. You can design the system in the S domain. With discretization you can change this one SSZ, this one the transfer function in the Z domain by discretization, or directly you change your system to the Z domain, design the controller in the Z domain. Okay.